It's muted. Now it's better. Yeah. So thanks a lot for the organizers. Now we'll switch gears a bit. This will not be a science talk per se, but more of a science infrastructure talk. My name is Rasmus Kronberg. I work as a computational chemistry specialist at the HPC company providing the supercomputing infrastructure in Finland, CSC. I will be talking about AI and material science on the LUMI supercomputer. So what is LUMI? LUMI is a pan-European HPE Cray EX supercomputer. Looks like this. It is about the size of 2 tennis courts and with a computing performance corresponding to roughly 1.5 million consumer laptops. And this makes LUMI the 3rd fastest supercomputer in the world currently and the fastest one in Europe. Looking more closely, by the way, please don't mind the unphysical 8-pointed snowflake. This is just branding. But LUMI is composed of 8 different partitions, and the majority of the sustained performance of 375 petaflops comes from the LUMI G, so the GPU partition with more than 10,000 AMD Instinct GPUs. In addition to this, LUMI has an auxiliary CPU partition of about 200,000 AMD EPYC CPU cores. This is about the same size as the Mahti supercomputer, if you are familiar with the national supercomputers of Finland. In addition to this, we have partitions for data analytics, storage, and then also some upcoming features such as an object storage service, LUMI O, a container orchestration platform for microservices, and then a quantum computing environment, LUMI Q, which will be hosted by the Czech Republic and then integrated into LUMI. So LUMI is hosted and maintained by CSC, but it's not owned only by CSC. It's owned by the Euro-HPC joint undertaking. And this is really a unique collaboration between 10 European countries and the EU. And we have the total budget of the LUMI project is more than 200 million euros. And it's really the first co-investment ever of this scale in scientific computing. The resources that LUMI provide are divided to all the LUMI consortium countries based on the investment put in, and 50% is owned by the EU, so that's an allocation that any European country can get access to. In addition to this, the LUMI consortium provides training, support, and data management services. So because LUMI has both GPUs and CPU partition, the sort of aim is to provide really a cutting-edge research platform for coupling artificial intelligence and high-performance data analytics with high-performance computing and more traditional simulations. So what LUMI can provide for AI, the first thing that's important to note is that LUMI is powered by the AMD GPUs, and this then comes with some changes compared to NVIDIA GPUs that I guess many of you might be more familiar with. So instead of the CUDA programming language, AMD GPUs come with the AMD programming environment, which then is branded as ROCm, and ROCm has the HIP programming language, which then replaces CUDA. Similarly, for example, the CUDA deep neural network library of machine learning primitives has the MIOpen counterpart in AMD software stack, and also, for example, the NVIDIA collective communications library has the ROCm collective communications library RICL as a counterpart. In addition to the AMD software stack, LUMI comes with the full Cray programming environment, CPE. And here the highlight for artificial intelligence is the CPE deep learning plugin which is a communication package that is especially optimized for deep neural networks and deep learning. So overall, I would say that the situation for running machine learning frameworks on AMD GPUs is in very good shape. So ROCm versions of the standard frameworks like JAX, TensorFlow, PyTorch are readily available and they run really well. So we can, for example, look at the example benchmark where we have been fine-tuning the GPT-2 model with PyTorch, and compared to an NVIDIA A100 GPU on the Mahdi supercomputer, this takes on one GPU about 18 hours, and then on LUMI on one AMD MI250X GPU, it's almost half the elapsed time to do this benchmark. And scaling this up to 128 GPU nodes, that is 512 GPUs, we still get very excellent scaling. So the performance that we have seen so far is really promising for the artificial intelligence workloads. One thing perhaps to note here is that the AMD GPUs are composed of two graphics compute dies. So in principle, you can think of one of the AMD GPUs as sort of two GPUs, and you can use sort of half the GPU at a time. And in many cases, we see that even one of these graphics compute dies is as fast as one NVIDIA A100 GPU. Looking then at material science, we can separately consider classical molecular dynamics and DFT. So on the classical side, software such as GROMACS, AMBER, and LAMMPS have been ported in one way or another to AMD GPUs. For example, GROMACS and AMBER have heap patches made by AMD specifically that allow them to run really efficiently on the AMD GPUs. And in LAMMPS, for example, we have the COCOS programming model, which is used to enable LAMMPS to be run on GPUs, and this includes also AMD GPUs. Typically, what we see is the same as for the artificial intelligence workloads when we look at a single GPU. So the performance is really good on one graphics compute die. It's even sort of typically outperforming a modern 128 core CPU node, but the scaling is something that still is sort of not that good. So typically we are limited to maybe one GPU node or just single GPUs, but this really opens the avenue for high throughput computing and task farming to maximally utilize the resources. So if you're able to run your workflows such that it's composed of practically independent simulations, then firing these on many GPUs in parallel is of course something that will work. The AMD GPU support for DFT codes is perhaps slightly more in development. Typically, most of the major DFT codes have support for NVIDIA GPUs at some level, but the AMD support is getting there still. So we have seen quite good developments in the CP2K code, for example, as well as Sirius-enabled Quantum Espresso, GPOV. And then as a nice example is the TurboGap code, which is actually developed here in Aalto by Miguel Caro's group. Here we have a specific project, ExaFF, in which we are porting this program, which allows you to run gap simulations to AMD GPUs. Typically, the case is that only some of the features in DFT codes are able to run well on GPUs. So, for example, in CP2K, the linear scaling part is something that runs on GPUs, since it has some is centered around sparse matrix multiplications that can be optimally offloaded to the GPUs. Here is one example of a benchmark running LAMMPS. So it's a 16 million atom copper lattice embedded atom method molecular dynamic simulation. And as said, we can see that on one full CPU node, we have a performance of about 2 nanoseconds per day. And this is surpassed already by using one graphics compute die, so half a GPU. and we get quite nice scaling all the way to a full GPU node. But then slowly we start to see a decline in the performance. Some examples of pilot projects that have been run on LUMI during the LUMI G pilot, which ended just a couple of weeks ago actually. Thijs Wegge and co-workers for Denmark have been within the Big Map project, battery interface genome materials acceleration platform, been running or training some deep neural networks to predict electronic structure data at a very high accuracy related to battery materials development. Jörg Hutter from University of Zurich and his co-workers have been doing really impressive double hybrid DFT-MD simulations of solid liquid interfaces, for example. And then Nicola Marzari and co-workers from EPFL have been doing what they call an AIDA hero run with Sirius enabled quantum espresso, basically orchestrating a very large number of first principles calculations using the AIDA framework. So LUMI has software pre-installed, and due to the size of the computer and the number of users, it's perhaps slightly more limited than the Finnish users might be familiar with Puhti and Mahti. The sort of central software stack is then augmented by software collections that are maintained by the local organizations, so the individual countries in the LUMI consortium. But in addition to this, we try to make installing your own applications on LUMI as easy as possible. So we have the easy build framework and a lot of recipes optimized for LUMI that you can use to install your favorite software on the supercomputer. And also, if you are more familiar with the SPAC package manager, then this is something that's available, but there's no sort of specific package development for SPAC. Then also, with dealing with Python environments, we have a very handy tool, the LUMI container wrapper, available, which allows you to package, for example, Conda and pip environments in a container, which can be then run very efficiently on a parallel file system, such as LUMI has. If you have used Puhti and Mahti supercomputers, you might be aware with the Tykky tool. So this is exactly the same tool. It's just a single command to install and containerize a Conda environment, and then you can basically call the binaries that are installed as if they weren't containerized at all. There's also a lot of upcoming features, so LUMI is not ready yet. For example, we have the LUMI web interface coming up, so there will be a way to use the supercomputer just from the browser. And this is a very nice opportunity to run, for example, Jupyter Notebooks or RStudio on the supercomputer from your browser. Also, there has been some plans to make available some curated reference data sets in a sort of spirit of datasets as a service. And also the LUMI K partition will enable you to run microservices on a Kubernetes cluster with access to the parallel file system. And then, of course, there has been some plans to make CI/CD pipelines available for model and dataset versioning. So if you're a Finnish user or affiliated with the Finnish university, then there are 3 different access modes, how you can get access to the LUMI supercomputer, and you can apply at any time from this MyCSC portal. In addition to this, we have extreme scale calls once a year for really large resource requests or needs. For users not affiliated with a Finnish university, so the other LUMI consortium countries, or then if you're from a European country not part of the LUMI consortium, we have instructions on the LUMI website how you can get access to the different countries' allocations as well as the EuroHPC allocation. Documentation, training, and support is available in the LUMI docs as well as the LUMI website. And here also the CSC's own documentation and CSC training pages and the CSC service desk complement this service portfolio. One addition with the LUMI is that 20% of the resources is actually reserved for European SMEs and industry. So I think there might be a few company representatives here as well. So if you're interested in taking LUMI into use, it is possible. If you're not affiliated, but collaborating with a university or a public research institution, and the results of this collaboration will be published, the computational resources will be actually free of charge. Otherwise, there will be a market price then. The EuroHPC JU allocation for non-Finnish companies is also there for pay-per-use usage of LUMI, but also we have European funding programs and also national funding programs for, especially for SMEs, if you want to get try out LUMI. And we actually employ this sort of try and buy concept that you are able to test the system and then invest only after you have tested if you want to do so. So here you can either contact directly CSC service desk or then look at our business pages on the CSC website. With this, I'd like to conclude and thank you a lot for your attention.
Okay, thank you, Rasmus. Do we have questions, Rasmus? At the back.
So if I understand correctly, this is based on applications, correct? So I'm interested in how many applications, so what is the rate of success? And if you already need to prove, let's say, how your code is scaling on your specific hardware.
So as an academic user, are you an academic user? Yeah. So I actually can't speak now of the other LUMI consortium countries, but at least in Finland, the application rate, the success rate is basically 100%. So there's a lot of resources available, and I'm sure that if you apply for computing time from LUMI, you will get granted. The EuroHPC allocation. Yeah, I think also there. So just apply for the resources, and I would be surprised if you don't get it. Yeah.
While we wait for the mic to come, do you know roughly what applications are run on the LUMI GPUs? Is this mostly machine learning? Or?
So of course, machine learning is in the best shape with the sort of, because I mean, the initially how most of the machine learning frameworks have been developed is to be run on the GPUs, and actually going from NVIDIA to AMD is not that hard actually to port the code if it's already in the beginning to start with implemented for GPUs. But then the problem with first principles codes, for example, is that they might have been developed really a long time ago, and sort of porting the whole code base, which might be millions and millions of rows of Fortran, then that to GPUs is a problem, and that's why the development is taking more time.
Melissa.
So a quick question. Thank you, Rasmus. I think you made us all very happy with this talk about the resources. Something that is very unique about LUMI is the diversity of the different partitions. And have you done any tests or any pilot studies on combining CPU and GPU partitions in the same job?
I'm not aware of like specific examples, but this is for sure one of the aims. So this is the whole idea of having quite a hefty CPU partition sort of flanking the GPU partition as well, that you would be able to both run your more traditional HPC cases that perhaps won't work that well on GPUs, but also utilize then the GPU partition for machine learning workloads and combining that for sure. Yeah.
Okay, I see no further questions. Oh, there's one. Matthew.
Yeah, thanks for a lovely talk. Relate to what you're saying about porting DFT codes like away from CUDA to whatever this new system is. Is this going to be the final time we need to do that? Or, you know, we've seen all these sort of like OpenCL and all these other various attempts to make open source like GPU stuff. And I know NVIDIA kind of has their means of controlling that market a little bit.
Yeah.
Is this the one, or are we doing the same thing in 10 years' time?
That's a great question, and I can't foresee the future. But of course, we have Intel, of course, which are trying perhaps to do some of their own developments, and but currently, I mean, AMD and NVIDIA are the two big ones, or AMD is trying to become one of the big ones together with NVIDIA. So I would hope there wouldn't be new sort of frameworks and paradigms coming, but then we have the quantum computing era coming up, and how you interface the sort of your code, which maybe is partly run on CPU, partly is offloaded to GPUs, and then you partly offload it to QPUs. So I would sort of, there probably will be some new sort of efforts coming up still that you need to put. But I mean, this is how it goes. Things develop.
Okay, good. We have to move on to the coffee break now. So let's thank Rasmus again. We're about 5 minutes behind schedule, but I'd say let's stick to the 20 minutes and then come back here at about 1:45.